I will tell you about the Bolt and how we built it and all the challenges that we met along the way, how it's constructed, all that sort of technical stuff. And yeah, to start off with the requirements, because as we said, we needed something to test, to load test the applications that we were testing against. And it had to be easy to use and maintain. That's definitely Locust. It had to be customizable, easily customizable. That's definitely Locust again. It had to be host resources independent and scalable. And what that means is basically, yes, of course you can run Locust on your local machine, but that will put a huge stress on that machine. And also the results, they're not going to be consistent enough because it all depends about the background load of your, usual workload of your computer. And we were supposed to address that. And also, the result sharing had to be easy. Locust also gives you this ability to spit out the CSV of the execution with all the results and all the data. But emailing that stuff around each other, it's not an ideal solution. So we had to address that as well. And this is basically how Bolt is built, easy, right? And yeah, so let's go step by step. This is the breakdown and the abstract requirement from the bird's eye view. We have a user on the left that puts Locust tests. Then these tests are going to be performed in the cloud among the various workers. And then that gives us the results. So this is the core structure at a glance. This is super basic stuff. What we see here is users interacting with the Bolt portal, which is the front end of the application. And that front end is communicating with Hasura, which is serving us the GQL, the GraphQL communication. And it's using Postgres as its retention service. And then at the bottom, there is Bolt API, which is basically a Flask application extended with the GraphQL compatibility. And so to put all that and sort of like depict it as this Bolt block, we again see user, which is interacting with Bolt, which is interacting with Argo, which then grabs tests from the test repository. And you might ask, what is Argo? Argo is a big project. It consists of many tools. What we are going to focus on in this presentation is specifically the Argo workflows, which lets us define, automate, and execute flows in Kubernetes, so the cloud service. So we have our scalability. It's also cool, it's open source, it lets you build complicated CI/CD pipelines, and most notably the workflows. Here on the right, you can see the screenshot of the actual Bolt execution. Here you can see the execution is branching out. What this branching means is that we have one load test master and multiple workers. This is just an example. This can be much more, extending to the left and right. There may be many, many more workers. And moving on to breakdown, this is what the structure looks so far. So to kind of fuse these two graphs together, we see user, which is storing some tests, probably Locust tests in the test repository. But then user interacts with Bolt portal, which then instructs Hasura to start off tests using Bolt API, which instructs Argo to spin some pods in the Kubernetes cluster. So what actually does make it work? And underneath all that is Locust. This is basically the GUI of Locust, really super simple stuff. You'll have only like 3 fields here. As Jan already said, it's open source, it's a load testing tool, it's easy to use, and it lets you scale up. This is a sample execution from Locust. We can see some major data that is being pulled from the execution here. And again, this is like an example test written in Python. This is an actual working test. Like, you don't need much to make it work, which is what we needed. To kind of put Locust in a picture, you can see on the right there is a graph. It depicts the master node of Locust, which kind of orchestrates all of these inner workings of the load test. In the middle, you have n number of workers. This can really be depending on what you need to achieve. And on the bottom, there is a service, an application that you're testing against. Again, Locust is open source. It's really versatile. It's easy to use because you're writing tests in Python, which is super simple. It lets you scale up. That's the scalable part because you can have many, many workers. And it has event-based construction, which we can sap into to kind of put our own custom code into. And we also have a full control over user per worker distribution, which is going to be necessary later. So to fuse all these graphs together, we now have this. To not go over every detail, as I already did, what Argo does is it spins up pods in the Kubernetes cluster. Some of these pods, notably one, is a master node that orchestrates all this stuff that is happening during the tests. And we have n number of workers, which is basically every single worker is another pod. So, load distribution. And again, there is an application that we're testing against. But there is also another arrow going through Hasura and masternode, and that is arrow depicting the exchange of the information, the results between masternode and Hasura. But you might ask, okay, we need some code to actually run all this and automate all that. We need to have context. And that's where the Bolt Image Builder comes in. This is, again, our custom code. What Bolt Image Builder does, it takes the test from the repository, from the Locust repository. It takes Locust itself. Locust is a Python package, so it needs to be pulled up. Then other dependencies, as Johan already said, you can put your own code, your own packages, your own requirements to the test, and that will be automatically pulled in. And also there is the Bolt wrapper repository, which the Bolt wrapper pulls its code from. And all that comes into this layer construction. On the very top, you have Python because something needs to be executing all this code. Right there on the bottom, you have Bolt wrapper, which kind of takes care of the whole communication stuff, load distribution, giving you some context to whether the Locust node needs to be a master or a worker. It needs to be knowing what to do actually during the tests. And then at the very bottom, you have tests. Moving along, this is where the Bolt Image Builder comes in. It's also executed in cloud. It's another pod. And then again, to reiterate, Argo is orchestrating the image builder, is ordering image builder to produce an image. That is where the user Locust tests come in. That is being pulled, and the ready-to-use image, that is whether going to be a master node or a worker node, is then being put into Google Cloud repository and fed back into Argo. And then Argo takes that image, and it uses that context to sort of run the application itself. But wait, there's more. And that more is, it's good to have a full picture of the situation, and why don't we use the built-in, the service that we're testing against probably has a Prometheus server running. So we can kind of sap into that and not only know what is actually happening from our perspective to the service that we're testing against, but if we have accurate data from what the server itself, or the application itself, is telling us what is happening to it, that's even better because we have a full picture of what's actually happening. So there's another pod that is being run in the same cluster that kind of connects to the service that we're testing against, connects to its Prometheus server, pulls that data, and puts it back into Hasura under the same context of the same execution that we're running. And on top of that, we can generate the ready-to-use, ready-to-send PDF report with all pretty graphs and whatnot, because that's also a custom code. And store that into Google Cloud Platform as well, and serve that to user via the Bolt API. And now there is a good question to ask: data and why there's so much of it. And that's actually a stupid question, because the only answer that comes to my mind is, too much data is better than not enough. You know, it's kind of this conundrum. And you know, we have layers upon layers and layers and layers of data, and there's really a ton of it. But you know, the more data you have, the more challenging it is to kind of put that data into use, to have some context out of it. And here you can see two graphs. There's going to be more. Two examples of what went wrong. I mean, we didn't really know what is going on with the application itself. We wanted to build a highly scalable application. We were trying to parse all these numerous amounts of data. And the results were like, okay, so we can see that this graph is empty. Apparently no requests per second were produced. The response time is 0 milliseconds, and there was some kind of, there was 1,000 users during this execution, but this doesn't add up. Something went wrong. Here at the bottom, you can see some interesting flatlining here. After 2.5 minutes of the application running, all of these graphs started to flatline. Something bad happened. And also there's been like a weird spike here. Maybe this has something to do with it. And also notice the user spawn. There's this graph should be like going straight up, rocketing up, but it doesn't. It just, it vibrates. Again, something's wrong is happening here. And even more examples. Again, flatlining, no successes though, even worse. And here, some dips, some spikes. Although user spawn seems to be completely good, well, something wrong happened. And this was kind of the moment in the both development that it was kind of the to be or not to be of the application, really, because the requirement to be, it was to create this highly scalable tool for load testing. But if we're trying to scale up, then we're like, toppling down, everything breaks. That's not good. And so the huge and lengthy process of introducing numerous improvements started. The first thing that we did was to introduce the supervisor into the Locust master node. What this means is that, as I already said, Locust is based on G-event and events. And expecting one node to orchestrate all this work that all these workers need to do, I mean, it's not heavy lifting. The workers do that. But then again, there's so much data that we're pulling in that we need to kind of separate these tasks, because if master node was busy with communicating with the nodes and it wasn't sending the data back and all the timestamps were wrong and all bad things started to happen. Thus, we started getting these erroneous executions. On top of that, there were many, many more improvements, but I will talk about only these through briefly. So, first of all, internal Locust challenges. As I said, G-event, but on top of that, SSL verification. We noticed that we cannot just run the same tests against servers and applications that are hosted with SSL verifications. If we change the host to be HTTP instead of HTTPS, then everything was kind of fine. But if we did it like on the other way, then the whole structure was toppling down because of how Locust is handling the SSL verification. We need to work our way around that. Also, the redundancy follow-up. There is the CSV dump in the parentheses. So what this means is that you need to understand that the development of both was a lengthy process, and kind of the usage of Locust changed over time. There were some improvements, some changes, and addressing all these forgotten areas around Locust was one of the improvements. So that was really, really important. And on top of that, I think there is the. Oh, no worries. Okay, so basically, all these summed up gave us the solution for the domino effect, that is premature worker death. What this means is basically when one worker was busy with some work, maybe the response message was kind of lengthy because it was an error, then it was busy parsing that JSON object that got returned in the request, and it was trying to figure out how to send all that information back to the master node. And it wasn't really working because, again, all the timestamps were wrong because we were aiming at the millisecond precision. And the request was sent out, came back, but the worker wasn't like really telling master node that it was done with that request. And that caused that worker to fail to respond to the heartbeat that master node was sending back. And that worker was dying because master node was like figuring out, okay, so you're not responding to me, then that means you're probably dead. And it was spawning another worker, and thus the vibrating users node the graph. Then was the data desync and data accuracy. Those two were solved by the supervisor because we were lifting the heavy load of the master node. It didn't really have to do much work to send out all the information back to Hasura for us to parse later. And then we started seeing nice patterns in code. Finally, all these successes and requests and bad status codes and whatnot, all these error or not, everything was syncing up and to the millisecond precision. We also started seeing another patterns. Here you can see, I think it was Flask we were testing against, which is really interesting because you don't really see that much if you're not using a proper tool to interpret your results. And here we can see that Locust is kind of like starting to cache the requests at the very beginning of the test execution. So if there is too much requests, then Flask is like doing this huge QE up until after 4 minutes, the response time grows up to over 200 seconds, which is kind of bad, but you wouldn't be able to see that otherwise. And all these graphs started to make sense again because we can see 20,000 users, flat line, and the request response time is a nice graph going up, again corresponding to probably this one because there were a few requests that were 200 seconds long, and some of them were at the millisecond level. And so the median and the average response time averaged about 2 seconds here. And then again, the requests, total number of requests per second were equal to the fails and successes. Pretty cool stuff. And here is the actual execution to sort of show you that we're not, these are just not words, this is actual data. This is basically showing the number of requests with number of successes and some errors on top on the same graph. But in order to see the pattern, because as you can see, here are some spikes. 150 bytes, another 300 bytes here. We don't see any correlation between these two. So probably there must be a correlation between these two graphs. And so if we take out requests out of the picture and zoom in down on failures, then we can see that the failure was 150 bytes long. And that is basically kind of a proof that, we really started getting actual data to the millisecond level precision. And again, this is Prometheus metrics to sort of show you what is actually going on with the application, ask the application itself. And again, you can dig into these graphs and see some correlations, scientific stuff. And on top of that, you can get all that. If your boss is picky, you can generate the PDF report and send it to him as a proof that the execution took place and the application is maybe stable, maybe needs some work. And that begs the question, how fast is fast? And at some point, when we started seeing that the application is starting to work as we want it to, then we need to kind of test this speed. And I really wanted to show you a commercial of one car company, but I'm not going to be able to because of the licensing and stuff. But I took some screenshots out of it. Maybe some of you remember it, maybe not. So we see the rocket car speeding up down the desert really fast. Yeah, we can see that the car is stopping down by deploying a parachute, really high speeds. It slows down, it comes to a stop, and then the fourth wall is broken because there is a guy in the camera and basically in a driving suit. He did not come out of the rocket car. And then the camera pans out, and we can see that the rocket car was actually being filmed by something, by the camera attached to just a sedan. And it's sort of a challenge started, because we needed to find a service, a technology that would let us. Basically, we had that rocket car. We needed a sedan with a camera to sort of test things out. And the worst one, yeah, it was Flask. You can really go slower than that. So this is our baseline. And it was really an eyeballing situation, because we needed to have some sort of baseline, and that baseline was a test that takes 4 minutes, and it's 10,000 users trying to topple out on the 10,000 users mark. And Flask, in these 4 minutes, was able to produce 171 successful responses. Really, really low. But then again, there was Puff, which was almost twice as much, at 344,000. Puff is a really interesting project. If you want to check it out, the address is here. You just need to find Puff, basically. And Puff is a sort of amalgamation between Rust and Python. It gives you the speed of execution of Rust, but also it gives you the fast development of Python. You basically write whatever you want in Python, but the Rust application is actually running it in its environment. That's why it's such an improvement, twice as much. Then there was Node, interestingly, only 430,000. Then Golang, 443, not that much faster. And our black horse was Rust at over 500,000 requests, successful requests produced at 443,000. And we had our winner and started testing both against that. This is the comparison of all these executions. Here at the bottom, you can see Flask, which is, again, sort of interesting stuff to see how software behaves at higher loads. You can see that the Flask stopped at 8 seconds, and it was keeping that level consistently. Then we have sort of twice as better Puff, but the response times are, is there a dot or is it not? No, it's actually faster. It's actually 4 times faster. But the number of requests per second seems to be lower. It's coming up at 800. So it must mean that Flask application was having some dips in the background. Then you have Node, which stopped at 6 seconds, and then something interesting is happening here, because this line is going down. So maybe some sort of caching started. And the same trend you can see in Go and in Rust. And definitely, you can see what produced such a good result of Rust, because the slowest response time was lower than 1.5 seconds. And that's pretty much it that I wanted to show you. Do you have any questions? No?